Hello, and welcome to Differential Equations. This is lecture 18, Damped Vibrations. Last time, we talked about a mechanical system, which we could think of as being modeled by a cart, right, with some mass that's been displaced from equilibrium some distance x, connected to, say, a wall with a spring. And so then using Newton's second law of motion and Hooke's law, it's governed by this differential equation, and hence has solutions given by linear combinations of sine and cosine of omega naught times t, where omega naught is the square root of k over m. Right, so we see that if you move the system from equilibrium, then the system will oscillate around the equilibrium, right? It always moves towards the equilibrium, but it goes past, it has to go back. This time, we will introduce into this model a damping force. Okay, so the viscosity of the medium through which an object moves, right, be it air, water, oil, whatever, exerts a damping force usually modeled as being opposed to the force and having magnitude proportional to the velocity. So our damping force would be something like minus gamma dx dt. For example, mechanical systems often include devices for cushioning damping movement, known as dashpots. For example, you can put a piston in a cylinder containing oil. And then the viscosity of the oil will dampen the movement. Right? So this word dashpot One possible etymology is that dasher was an old-fashioned word for plunger, and the pot refers to the oil reservoir. So you can imagine that you have this cylinder with oil in it, and then you have like a piston going up and down inside it, right? And so the oil is going to make the movement um, of the piston dampen. Screen doors frequently have a dashpot to keep the door from slamming shut, right? It's usually a one-sided dashpot so that you can open it freely, but then as it returns, it slows down. Shock absorbers, or just known as shocks, in car suspensions are also dashpots. In the absence of external forces, Newton's law becomes m times x double prime is equal to the force, right? Force equals mass times acceleration. And now let's say the force has a component from the spring and a dampening component. And so we would get for the spring from Hooke's law minus k times x, and then from the dampening minus gamma x prime, right? So that means the equation we're looking at is m x double prime plus gamma x prime plus kx is equal to 0. Okay, this ODE has a characteristic equation m times r squared plus gamma r plus k equals 0, which has roots r equal to minus gamma plus minus square root of gamma squared minus 4mk divided by 2m, right, which we could also write as minus gamma over 2m plus minus the square root of gamma squared over 4m squared minus k over m. And so the behavior of the solutions to the ordinary differential equation will depend on the sign of gamma squared minus 4mk, right? The term inside the square root. Okay, so we have 3 cases to consider. First case, what happens if gamma squared minus 4km is negative? Right, so you can think of this as being the case when the frictional force due to viscosity is small compared to the stiffness of the spring. Right? So here are solutions are linear combinations of e to the minus gamma over 2m, right? So this is the case when this is negative, which means that this term is purely imaginary and this is the real part. So we have this exponential term out front, and then we have a sine or a cosine, right? Where the angle is given by the imaginary part times t. So it would be square root of k over m minus gamma squared over 4m squared square root times t, right? And the other terms would be the same, but with sine instead of cosine. Okay, so both of these are exponentially decaying oscillations, right? That's because we're considering gamma to be a positive constant. And so this exponential term, oh, for which I left out the t, sorry. This exponential term is going to decay as t increases. This case is called underdamped. Because of the sustained oscillations. So even though the oscillations will get smaller and smaller as time increases, you still have infinitely many oscillations going on. And so it's called underdamped. In mechanics, let's say in mechanical systems, such sustained oscillatory behavior is usually unwanted. Okay. So second case, what if gamma squared minus 4km is positive, right? So this is what's known as the overdamped case. So here the roots of the characteristic equation are these two real numbers, gamma squared minus 4km root, right? So if you have when you take the plus sign, let's call it R1. When you take the minus sign, let's call it R2. So these are two distinct necessarily negative numbers. And the solutions, well, let's say in the general solution, the ODE is just some constant times e to the R1t, some constant times e to the R2t, right? R1 and R2, negative constant. So that's exponentially decaying. And then the third case, when gamma squared is equal to 4km, or let's write it as gamma squared minus 4km is equal to 0, this is what's known as the critically damped case. So here the characteristic equation has a single root r equals minus gamma over 2m with multiplicity 2. And so solutions of the ODE have the form A times e to the minus gamma over 2mt plus b times t e to the minus gamma over 2m times t. Right, so in most mechanical systems, one would like to be in the vertically damped case or slightly overdamped. Okay, so now let's allow for an external force which, like last time, we're going to assume is just a very simple periodic function. So we're going to assume it has the form some constant f naught times sine of omega t. Okay, so that modifies Newton's law. So then now we have mx double prime plus gamma x prime plus kx is equal to f naught sine of omega t. So this is a second order linear ODE with constant coefficients, but it's non-homogeneous. And so we need to find a particular solution. Okay, so this right-hand side is very simple. So we can and should just use undetermined coefficients. So let's just try for a particular solution of the form little a times cosine of omega t plus little b times sine of omega t. Okay, so if we just plug this in, right, we have mxp double prime plus gamma xp prime plus kxp. Okay, and we know that if you plug in sine or cosine, take two derivatives, you're going to get minus the function you started with. If you have, say, sine of omega t, and you take two derivatives, you're going to end up with minus omega squared times sine of omega t. And of course, that's also what you have from your particular solution. So we can, from the first and last term, we get k minus m omega squared times x of p. And then from taking one derivative, we'd get plus gamma times omega times minus a sine omega t plus b cosine omega t. Right, so if we group together the terms with cosine, we're going to have k minus m omega squared times a plus gamma omega times b, right? That's times cosine omega t. And then the terms with sine, so minus gamma omega times a plus k minus m omega squared times b, right? Multiplying sine of omega t, right? And then we want that to be equal to f naught times sine of omega t. Okay, so that leads to a system of equations, just comparing coefficients of the sines and cosines. Comparing coefficients of the cosines, we want this to be equal to 0. And then comparing coefficients of the sine, we should have this equal to F naught, right? This system has a unique solution as long as what I'm going to call capital D, K minus M omega squared plus gamma squared omega squared is not equal to 0, right? Notice that, of course, this is really easy for this not to be equal to 0 because it's a sum of two squares. So both of these are positive or non-negative terms. So this can only be 0 if both of these were 0. So we would need to have gamma equal to 0 and omega equal to the frequency we found last time, square root of k over m. Okay, so as long as we have some actual dampening, if gamma is not equal to 0, then this capital D is not equal to 0. So there is a unique solution. That unique solution is little a equal to minus gamma omega F naught divided by D. And little b is k minus m omega squared times F naught divided by D. And so we can write down our particular solution. Right, x of p of t. And so we can pull out as a common factor here, d shows up as the denominator, f naught as the numerator, and then we have minus gamma omega times cosine omega t plus k minus m omega squared times sine of omega t. Okay, so that's our particular solution. This is often expressed a little differently. xp of t. So out front, I'm going to have a very similar factor, except I'm taking the square root of the denominator now. And then I'm going to have sine of omega t minus phi, right? And here phi is going to be arctangent. In fact, let me write it out as arctangent of gamma omega divided by k minus m omega squared. Okay, so let me put as a remark that rewriting the particular solution like this is not particularly difficult if we have any expression of the form a times cosine omega t plus b times sine omega t and then we compare it with the formula, say capital A times sine of omega t minus phi, right? If you just expand that out, you would get minus a sine of phi times cosine omega t plus capital A cosine phi sine of omega t. Then we can arrange, right, for the coefficients to match. So you want minus A times sine phi to be equal to little a, and capital A times cosine phi to be equal to little b. And so all you need to do is take capital A to be the square root of little a squared plus little b squared, and phi to be arctan of minus a over b. Okay, so rewriting the particular solution we found in this form is not particularly hard. It's just a matter of convenience. Now that we have a particular solution, we know the general solution to the equation we were studying, right? M x double prime plus gamma x prime plus kx equal to capital F naught sine of omega t. Right, of course, it looks a little different depending on which of the three cases we're in. But for example, in the underdamped case, it is x of t is equal to capital A e to the minus gamma over 2mt cosine of, let's say, alpha t plus capital B e to the minus gamma over 2m times t sine of alpha t plus, so this term, k minus m omega squared squared plus gamma squared omega squared, all of that square root, and all of that below f naught sine of omega t plus phi, minus phi. With here alpha is square root of k over m minus gamma squared over 4m squared. And phi is arctan of gamma m over k minus m omega squared. Okay, so I wrote this all out just so I could point to it now. So note that the solution of the homogeneous problem is, we could call transient, in that it approaches 0 as t goes to infinity, right? So these first two terms, because we have this exponential with a negative exponent, as t increases, that goes to 0, right? Of course, that's true not just in the damped case, in the underdamped, sorry, that's true anytime there's damping. So in fact, that's true anytime that gamma is positive, right? So in the three cases we considered, we always had that. Therefore, as time goes on, the motion looks increasingly like the final term. That is to say, it looks increasingly like the particular solution that we found. Which we could call steady state, or the steady state part. Okay. Finally, it's worth taking a closer look at the amplitude of this steady state part. Right, so let's give that a name, amp. Let's think of it as a function of omega. So it looks like this fraction. Okay, so it's simple to compute the derivative. Right, so the derivative with respect to omega of this amplitude function would give you minus capital D to the minus 3/2 times omega times gamma squared minus 2mk plus 2m squared omega squared. So again, we have three cases to consider. If gamma squared minus 2mk is positive, right, then this term is the sum of a positive and a positive number. So it's always positive. That means that this derivative is always, well, it's negative. If omega is non-negative, then this is always negative. So we see that this curve has a global maximum at omega equal to 0. And decreases as mod omega increases. If gamma squared is equal to 2mk, then you can rewrite this amplitude as f naught divided by k plus m omega squared. So same sort of behavior. Right? Namely, it has a global maximum at omega equal to 0 and decreases as mod gamma increases. Right? Notice that, of course, this amplitude we said was the steady state. Right? So we're seeing how large are the oscillations that you're getting in the long term. Right? And so, well, a global maximum when omega is equal to 0, right, which is right, which is when you have a very simple periodic function because the angle would always be 0. And it decreases as the modulus of the angle increases. Right, and then finally, if gamma squared minus 2mk is negative, then, right, this term is negative. So here we have this curve has a local minimum. At omega equal to 0. And its global maximum occurs when omega is equal to plus or minus square root 2mk minus omega squared divided by 2m squared. Right, so that is when this term vanishes. Okay, and then finally, let's think about resonances. Remember from last class, we saw the resonance was what was happening when the amplitude was blowing up to infinity. So in this case, when would this amplitude go to infinity? So resonance here would occur only if this denominator was going to 0, right? But this is, so this capital D, remember, is the thing that we're taking the square root of here. So for that to be close to 0, this term would have to be close to 0, and this term would have to be close to 0, right? And that only happens if gamma is close to 0 and omega is close to the natural frequency from last time. Okay, so this is only happening when you have no dampening, and then it's the case we considered last time. Okay, so we'll stop there and pick it up from there next time.